Phasors, probability and all paths. We can imagine photons moving from A to B, carrying a phasor with them. The phasor rotates anticlockwise with the frequency of the light of the photon. The difficult part is that the photon tries all possible paths between A and B. Don't expect this to make sense, it doesn't. But it does allow us to make predictions, and it does match observations. The probability of the photon's arrival at B is directly proportional to the square of the sum of the phasor amplitudes for all these paths. More about this in a moment. Let's look at a very simple case of a source, as torch, and a detector. Photons carrying their phasors could travel straight from source to detector, like this. Or they could travel through any number of paths, for instance this path, and all other paths in between. Every photon tries every possible route. The phasors turn as the photon travels. The direction they point when they reach the detector depends on the path length. The longer they travel, the more turns they make. For every random wiggly path, there will be another path allowing an extra half rotation. So for every phasor pointing up on detection, there will be another one pointing down, like this. The sum of these phasors is 0. They add in the same way as vectors. However, if we just consider the phasors going straight, or almost straight, from source to detector, for example following the straight-through path, this slightly higher path, and this slightly lower path, then this might be the phasor direction for the bottom route. The central straight-through route won't have travelled quite so far, and so won't have turned quite so much, and will point in this direction. The top route is the same length as the bottom route, and so the phasors will have turned just as much, and this would then give the direction of the top phasor. The sum of these phasors going from tail to tip is this. These three phasors give a large sum, and so a high probability of photons being detected. So if we were to place two barriers between the source and the detector, as shown here, it would make little difference to the number of photons detected, as these barriers only prevent the random paths where the phasors would cancel each other out. The straight-through routes are still possible. We can explain Young's two slits in terms of phasors. Here we have our source, two slits, and a screen. And the photons could travel from source to screen through the top slit or through the bottom slit. In the centre, the path lengths are the same, so the phasors would be in line. They add to give a large sum, meaning a large probability of photons arriving here. This produces a bright region, which I'll mark here. But if we now consider the phasors reaching a point around about here, the one through the top slit would travel like this, through the bottom slit like this. Now the path through the bottom slit is shorter, allowing half a rotation less by the phasor travelling through the bottom slit. The phasors cancel out, giving 0 probability, so we have a dark region here. We can use phasors to work out how much brighter one area will be compared to another. First point A, the phasors might line up something like this. This is our resultant, with a magnitude of 5. For point B, however, the phasors might line up like this, giving a smaller resultant of 2.4. The probability of photons arriving is directly proportional to the resultant phasor squared. So for point A, 5 squared is 25. For point B, 2.4 squared is 5.8. So point A will be 25 over 5.8, or 4.3 times brighter than point B. Photons have 4.3 times greater probability of arriving at A than they do at B.